So the next part of the activity is to find the rotational inertia of just the platform itself. Again, there's a screw part here. That's going to want to fill that into the notch there. So that's what I'm going to do. Put that in and we lock that up. Okay, so make sure you slide all the way in and we'll repeat the setup. Now, they mentioned this before, but what you want to do is try to have this line to be parallel as possible. And now what you want to do is to measure the acceleration of the hanging mass. So for just the hanger, I'm going to try 150 grams. We'll see what happened here to the speed. The object, you don't want the hanger to be jumping around because that's going to give you the data's not going to be as smooth. And we release, and that seems to be a more decent speed here. Okay, so we measure the acceleration of the object as the string unwind from the spool. You'll now determine the rotational inertia of the platform itself, and the rotational inertia of the platform would be the whole thing, the platform plus the axle minus the rotational inertia of just the axle itself. Rotational inertia of a point object, and this would be your point-like object, and you're just going to set this at the given radius. Okay, so I'll slide that on there, and the center would be the point. So if I put it here and tighten that up right in the middle, that would be about 10 centimeters for me in this case. Okay, and if you think about what rotational inertia is, right? If I have a point mass here and I give the object a force, it is going to accelerate. The acceleration will be proportional to the size of the force and inversely proportional to the mass of the object. So the mass is a measure of an object's inertia, is resistance to motion. The greater the inertia, the smaller the acceleration is going to be. Rotational inertia is the rotational equivalent, right? It's the object's resistance to rotation. So if I go ahead and wind this up, the object is not rotating at this point. It's not rotating. I apply a torque, which would be the tension times the radial arm, which would be from the center to where the string is. So that would be the tension times R, will be the torque, which would then cause the object to rotate. Now the object has some type of rotational inertia or resistance to rotation. It doesn't want to rotate. There needs to be a torque for it to rotate. How the rate at which it rotates, the angular acceleration will depend on the rotational inertia or the resistance to rotation. For a point particle, that is equal to the mass of the object times the distance from the axis squared. So it's not just the mass now, it's how the mass is distributed from the rotational axis. The further we put the object away, the more difficult it becomes to rotate this object. Okay, so that's rotational inertia. It's the rotational equivalent to mass. The more massive an object is, the more difficult it is to change its motion. The greater the rotational inertia of this system, the more difficult it is to rotate. So if I let this fall to the floor, right, you'll see that the object rotational motion is changing. It increases in rotational speed. Okay, now if I were to change the position of the object, not the mass of the object, but rather just the position of the object, and I move it outwards here, the mass remains the same, but the position with which the object is from the rotational axis has increased. Therefore, the rotational inertia has increased. The rotational inertia is the distance from the axis of rotation to the point where the object is located, right? That's R squared times M is the rotational inertia. So if I release now, you can see that the change in the rotational speed is slower. The rotational inertia has increased for the same object. Okay? Now, if I were to bring it closer to here, what happens now? Take a look at the rate at which the rotational speed changes. Okay. All right. So now if we want to compare our values to the theoretical value, mr squared is the rotational inertia for a point-like object, right? We would have to find the rotational inertia of this entire system, which would be the point object, distance r away from the axle, the platform rotating about the center, and the axle itself. So we take this entire rotational inertia and subtract out the rotational inertia of the platform and the axle. So the previous run that we did.